Okay, welcome, good afternoon. Okay. Okay. Hold on. Okay. So so today we're gonna continue with our next topic, crystal growth, uh, which is going to cover conversion of sand to polysilicon. And the second part later on, we're gonna look into the conversion of polysilicon to more crystalline silicon, right? So before that, we just briefly go through the video, the YouTube video in the notes that I've included before. So can you all see the YouTube page now? Okay, all right. I'm not sure whether you can hear this, maybe just a little bit. But anyway, I'm just gonna go through the a few points, a few things in the video. Then you can go back and watch later on your own. So this is a summary video by GF or Global Foundries, one of the top fabs in the world. So we have GF in Singapore. We also have GF in New York, right? So a couple of my colleagues from Silterra last time um, migrated to Singapore for GF. Previously chartered engineering, I think. Previously chartered semiconductor, not chartered engineering, chartered semiconductor in Singapore, and then become GF, and then some of my friends uh, would also move to New York from Silterra to join GF. Okay, so this is some summary of GF on the conversion of sand to silicon as a functioning integrated circuit. So let's just go through. Can you guys hear the sound? So that's the production line, okay? That's how the wafer fab production line looks like. Oh, no sound. Okay, no sound is okay. It's okay. Because I think the most I can hear is probably from my from my speaker. But it's okay. Let's just go to the visual content if you like. Then I'll explain a few things before we jump into each specific process. So that's how it looks like in the wafer fab. So this one, it says the circuit diagram is firstly made, just like what we discussed yesterday, the IC design. So those are the circuits that's going to be fabricated later. Then it will be manufacturing. So it starts from the sand into silicon. Hari ini kita akan go through the crystal ingot growth. So this is the slow pull or Czochralski process that I told you yesterday. So the small things are the impurities. Either you want to do it P or N. So boron for P, phosphorus for N, to make the silicon P or N type. So this is the gowning process. We're gonna go through this again when we talk about clean room. Baju dia macam baju nak pergi ke bulan eh. People call it bunny suit. Wafer fab calls this bunny suit. So those are the cassettes which packs the wafers. So typically each cassette contains of 25 wafers. So that's a robot arm handling wafers. That's the car system, CAR system. Dia automatic transport lah, automation lah ni ya. So wafer tu kita tak bawa ah. Car system ni akan bawa from one process to another process. This one, the yellow environment is lithography. This is where the circuits are printed using light. So it's printing by light. So now it's going through each process briefly. So this is photoresist, which is spun across the wafer. So that's the reticle. The top one is the reticle, which is the mass contains of the circuits to be printed on the wafer. So the red part there is actually the photoresist, which acts on exposure to the light. And then some parts are going to be exposed. Some parts are not going to be exposed due to the mass structure. And then you can remove certain areas selectively. Don't worry about the details yet. We're going to go through the every single detail in every process. So that's another area of the wafer fab. So it says it's going to ion implantation for doping process. So that's a robot arm handling wafers. So it can rotate, it can rotate around theta, can move around X and Y and theta and also Z. So there's so many rotations, there's so many movement of the robot arms. This is the impurities incorporation into the silicon lattice, just like what we learned in trace last time. So the orange ones are the open atoms. The gray ones are silicon. It's a huge fab. Okay. Usually in wafer fab, every single process is categorized as one specific department. Satu proses, satu department. Okay. Now it's talking about the interconnection by using copper. This one is talking about cleaning process to remove all the dust, contaminants, whether they are organic or metallic or some of the residues from the wafers. So that's the yellow one is a barrier on structure to avoid contamination, cross contamination. The orange up there is a copper layer. So now the copper is the top part of copper is removed due to some reason. We're going to learn this one later on. So it's forming interconnection. The moment your fabrication is almost done, the final step will be the interconnection to connect the device to the outer world. So these are all characterizations: SEM, TEM, optical microscope. We're going to cover this one as well during characterization of silicon wafers. So those are the detailed structures after the fabrication process. So circuitry is done in about 2 months of fabrication. So that's how long it takes typically. So the networks that you are seeing now is actually the interconnects, the final wires sitting on top of the device that will actually carry the current and will be measured at the final contact. So this is all about GF already. So okay, let us go back to the to the slide. So can you now see the slides? Okay, all right. So if you if you like to watch the video again, you can just go through the link later on. I think on page 6. So this is the exact link that I've played just now because you couldn't hear the sound. So that's basically sums up the whole fabrication process before we actually go to every single process. Okay. Two of you are waiting. All right. So now let's go to the topic for today, which is conversion of sand to polysilicon. Let me move this around first. All right. So like usual, before we move on to our current topic, let's just discuss on what we've learned yesterday. Um, so why is silicon chosen to make ICs? Why silicon for IC fabrication? Let's just recap a few things. Any volunteers, or we go by names? Fazira. Fazira, can you hear me, Fazira? Go Chingwei. Chingwei. Ah, Fazira, okay. Why silicon? Because silicon is a stable element. Okay, what else? What are the reasons for silicon? Kenapa guna silicon? Abundance, yes, abundance, good. What else? Why silicon? Cheap, yes. When it's abundant, it's cheap in comparison to others. Apa lagi? High band gap. When you compare to, yes, when you compare to germanium, yes, higher band gap, 1.1 versus 0.7, right? Other reasons? Ada lagi? Why do we choose silicon? Can operate at high temperature. Yes, it can stand high temperature. What's the maximum temperature silicon can handle? Izian, how high can you go? How high can you go with silicon? Can we operate at 2000? 1 to 5, 1 to 5 degrees C. All right. Can we exceed 1000? Boleh kah silicon kita exceed 1000? 900 C, okay. So it's actually in that region, okay. It can stand up to 1000, 1050, 1001 max, typically in a manufacturing process, especially when we talk about doping, oxidation, right? So you can't exceed, you can't go near to 1004 because silicon will melt at 1400 degrees C. Certainly not beyond 1400. Right. Why silicon wafer purity level is important? Why purity is crucial in fabrication? Kenapa kita perlu ada certain level of purity? Siapa ni? Aniza. Aniza, are you here? Aniza? Amira. Aniza, okay, right. To make it more defect tolerant, avoid recombination. Yes, okay, yes, makes sense. When you have higher purity, you have less defects. So when you have less defects, we avoid recombination, right? We don't want to have recombination. High quality device, yes, true as well. Kita tak nak ada high purity means low defects. Low defects means less recombination. Less recombination means high performance, right? So that's how it's related, right? What do you understand by IC technology node? What is IC technology node? When we say the technology node is 90 nano, what does it mean? When we say technology node is 45 nano, what does it mean? Apa maksud technology node? What does it reflect? Technology node means the gate length, okay, the gate length. So kalau you are talking about 45 nanometer process technology, so you are actually referring to the gate length or gate width or critical dimension CD yang saya dah tengok, saya tunjuk dalam apa slide first day tu. So it's referring to the CD or gate width or gate length, if you like, of the gate, right? So it's 45 or 32 or 22 or 14 or 10 or 7 or 5 or 3 or lower than that, right? So dalam when you look at the website of wafer fab companies, they don't really say gate length because that's that one is too technical for website point of view. So they normally say technology node or process technology. So technology node is equal to process technology is equal to gate length, right? So process technology and technology node is more like more layman. So if you are asked to draw a relevant schematic of this, then you have to draw CMOS, draw a CMOS with the gate on gate oxide on source drain, just like what we learned yesterday, right? On Moore's law, and then label your gate length, right? Okay, next, last one. What is Moore's law? Apakah hukum Moore? What is Moore's law? And why is it important? Liana? Liana, can you hear me? What is Moore's law? For anyone else? Number of transistors per square inch double every 2 years. Yes. Is it a law? It's not a law, okay? It's not a law if you compare to Newton's law, ke dia bukan law lah, but rather it's an observation, but it's called law anyway. So it says number of transistors will double in every 2 years. In every 2 years. Sampailah ke fundamental limit, right? So why is it important? Why do you think the Moore's law is important? So when we have the law, what's going to happen? Anyone? Shamim. Shamim, why is it important? You can unmute yourself. Kenapa law ini important? Any idea? Hazika? What we said, smaller transistor fabricated. Okay. So realize it or not, when you have the law made public, so what's gonna happen is that wafer fabs worldwide are trying to conform to the law, try to follow and try to deliver according to the law, right? So it's actually pushing the whole semiconductor ecosystem to deliver the next performing device, the next technology node, until we hit the glass ceiling. Okay, so that's why it's important. It's driving the ecosystem of semiconductor. Right, today we're going to look into crystal growth, which is the very part of the fabrication. This is gonna talk about the fabrication of silicon ingots and silicon wafers. So that's the crystal you can see there on the page. So what is crystal growth? So we're gonna talk about the growth process of silicon, which is going to cover two phases. The first one is going to be about conversion of sand to polysilicon, which is today, and the next one is going to be about conversion of polysilicon to monocrystalline silicon for use in fabrication, which is going to be tomorrow. Okay, so sand to silicon, you can go back and watch this. Pretty much the summary, like what you saw just now on the GF YouTube. Okay, so silicon is the most common semiconductor material for IC fabrication. So eventually we're going to talk about the conversion from sand into monocrystalline, but there are actually two processes, two main steps, I would say: sand to polycrystalline and then polycrystalline to monocrystalline. And the monocrystalline has to be of semiconductor grade or electronic grade, right? Dia bukan monocrystalline yang tak ada grade, right? It has to have certain level of purity. So when I talk about purity, the level of purity required by the monocrystalline silicon wafers are labeled as semiconductor grade or electronic grade, right? It's actually referring to 9N purity of the silicon required for the fabrication. Okay, electronic grade or semiconductor grade, they are actually the same thing. So it's referring to 9N purity of silicon. So 9N means 99.7 more nines. So you're going to talk about 9N. So if you talk about solar fabrication for solar cell, so 6N is good enough. So but 6N is not good enough for IC fabrication, but it's good enough for solar cell fabrication. So that means solar cell as a device is more defect tolerant in comparison to ICs, right? Because the complication and the requirement for the device to work is entirely different. It's a lot more complicated on the IC itself, but it's a lot simpler for solar cell. Metallurgical grade is a grade before the 9N or 6N is created. It's called MGSI, if you like. It's referring to 98.5 purity. So this particular 98.5 doesn't have any N to be specific because there's no 9999, right? So it's just 98.5. So when you see it's 98.5, it's actually referring to the purity of metallurgical grade silicon. So now, how do we produce electronic grade or semiconductor grade silicon or 9N silicon? So we know that sand contains tiny grains of silica. Sand is SiO2. So you can, to be able to fabricate silicon ingot and silicon wafers, what you have to do is you need to have sand in the first place. So that means kalau you have the sand as the precursor, so you have the sand and you have the equipment, you can actually fabricate your own silicon wafers. So sand is SiO2. So to be able to produce silicon with the right purity or 9N, so, the silicon dioxide or SiO2 has to be mixed with carbon in high temperature electric furnace to go through a process called carbothermic reduction, or it's actually a reduction process where SiO2 is reacting with carbon to produce the byproducts, and the outcome is a silicon. So the result is polycrystalline silicon. So it's not monocrystalline yet, it's polycrystalline. So kita dah belajar perbezaan antara mono dengan poly kan. So apa beza mono and poly? Apa beza monocrystalline and polycrystalline? You can type there. It says mono and poly. What does it refer to? Straightforward, right? Apa bezanya? Yang mana better in terms of grade? In terms of quality, which one is better? We've learned this in crystalline quality 386. Which one is better? Mono, right? Yeah, mono is better. Sebab mono tak ada grain, poly are the grain. So the moment you have grains, you have grain boundaries recombination and other stuff as well, right? So mono is better, but mono is more expensive. Okay, but unfortunately, the integrated circuit cannot work on polycrystalline. It has to be on monocrystalline. So we need to fabricate monocrystalline wafers then. So polycrystalline needs to be processed into monocrystalline to be used in ICs, right? Polycrystalline silicon is not enough. So there are 3 steps required for us to produce silicon or a semiconductor grade silicon of 9N purity. So the first one is called a carbothermic reduction process, where you can see the reaction there for row number 1, silicon carbide, which contains carbon, is reacting with silicon dioxide or sand, so to produce silicon, SiO2, and CO as the products, right? And then the moment you have your silicon from the first step, so then it has to go through a cleaning process or purification process where we purify our metallurgical grade silicon. So the first one is producing metallurgical grade silicon. So the MG silicon is going to go through a process with trichlorosilane. To produce trichlorosilane, it has to react with HCl. Then it will produce trichlorosilane SiHCl3 and hydrogen and heat due to the hot process. And then the trichlorosilane from the second row, from the second process, needs to be extracted and then used in the third step, which is called Siemens process. So this is the key process in the conversion. Okay, so the trichlorosilane is going to be reacted with hydrogen gas to produce silicon and HCl. So this is called Siemens process, which produces semiconductor grade silicon, right? So you have to be well versed with these 3 processes. So graphically, this is how they look like, the 3 steps. So the first one is the coke reduction. There you can see the coke reduction in an arc furnace at 1800 degrees C to produce MgSi. MgSi is the second here, the second step here. You can see the output there, MgSi, and then it'll be reacted with HCl, dissolve in HCl plus distillation process to produce trichlorosilane, and then it will go through Siemens process, which is this one, the key thing, the most important process, Siemens process at 900, and then it will produce a 9N high quality, high purity polysilicon by electronic grade. So the output from the third row just now is 9N electronic grade polysilicon chunks, right? Polysilicon chunks. So on the other hand, you can also do 6N to 7N if you go through this modified Siemens process, where it's not that energy and time intensive. So the first one, the Siemens process, is very high energy and time intensive as well. So that's why it is an expensive process to produce high quality polysilicon, electronic grade. If talking about solar grade silicon 5N or 6N, and the MGSI can go through this route for chemical refinement in order to produce 6N solar grade. But if you talk about IC fabrication, then our concern is only this one, right? If you talk about IC fabrication. So if you talk about solar cell fabrication, then it's going to be this, right? So it's going to be that line. Okay. So this is how it looks like for every process. The first row is now called carbothermic reduction. So look at the furnace there. So siapa ada cita-cita nak furnace macam ni, nak peminat lah kerja kat furnace macam ni. So you're going to work with 1500 to 2000 degrees C every day, right? It's an electrode furnace. So it's a very hot environment, hazardous environment due to the heat, right? SiO2 from the sand react with silicon carbide now. So that's simplified as carbon. So we'll produce silicon plus CO2. So the output there is MgSi. So you can see here, this one is actually MgSi, 98.5% purity. So carbon comes from the coal, coke, or wood chips. So high temperature process, 18 kilowatt hour. This is the energy usage, the electricity consumption for 1 kilo of silicon. So is it energy intensive process? If you look at this, 1 kilo silicon requires 14 kilowatt hour. How much is 1 kilo? 1 kilo satu pack gula kan? Gula, you pernah beli tak gula Pry? Satu pack gula kecil je. In order to produce 1 kilo of silicon, that much, so energy required is 14 kilowatt hour, right? So 14 kilowatt hour, right? That's a lot for 1 kilo only. And if you talk about ingot production, then we're talking about tons and tons of production, perhaps hundreds of tons, thousands of tons, right? The step 2 is called dissolution is ACL and distillation process. This is actually in row number 2 equations now. So silicon, MgSi silicon, so the first one here is MgSi. So it's reacting with HCl to produce trichlorosilane at 300 degrees C in an FBR, or fluidized bed reactor. This is the FBR. Impurities like iron, aluminum, boron will be reduced to less than 1 ppb, and then byproduct is going to be SiCl4, and then we're going to produce trichlorosilane, which is then purified by distillation process. So you can see the whole thing here. It's actually a huge plant for you to fabricate silicon. And then the last step is called Siemens process, the very last step, where the purified trichlorosilane is going to be reacted with hydrogen to produce polysilicon. So this one will be polysilicon 9N, poly 9N, right? Poly 9N. So silicon is going to be deposited onto thin heated polysilicon rods. So this is the rod. So this is the polysilicon rods. Yang besar ni. We're going to see in the next slide the image of the rods. So 150 to 200 mm in a chemical in a CVD chamber. So temperature is 1100 degrees C, and it takes about 200 300 hours for it to be done. So how long is 200 hours? 10 hari kurang 10 hari Satu hari 24 jam. 10 hari is like 240 hours, right? So, and therefore energy intensive. So if you put that into perspective, for 1 kilo of silicon, so you already need about 14 kilowatt hour of energy, of electricity, if you like. Then just imagine on the 1100 degrees C, 200 300 hours, hundreds of tons of silicon to be produced. So it's a lot. Right. The process was firstly developed by Siemens, so that's why it's called Siemens process. So it's been running like 70 years already. So it's still running this process. Now we still use Siemens process to produce monocrystalline for semiconductor grade silicon. But if you talk about silicon wafers for solar cells, there's a new process developed by one company called 1366 Technologies in Cyberjaya. Originally, it's a spin-off of MIT. So they are developing direct wafers to reduce the cost of the silicon fabrication. You can check it out, 1366 and all this, for direct wafer technique. They call direct wafer. Right, rods are then broken into chunks for crystal growth. So the polysilicon is going to be deposited on the rods, and then the rods are going to be broken into the chunks. Then remember yesterday I showed you the chunk which are going to be melted into liquid silicon for the Czochralski process. Right, so increase capacity by increasing the number of rods. So the more rods you have, these U rods, inverted U rods, so the more rods you have in the plant, so the more capacity you can produce. Okay, so new reactors have capacities of 600 tons per year. So that's a lot, 600 tons per year in terms of the production capacity. So this is how it looks like, Siemens process. So that's the jar. So those are the rods. So these are the rods, polysilicon rods 9N. Then it's gonna be broken into chunks. Ini belum patah, belum pecah habis ya. So this is poly 9N, poly 9N. So it's gonna be broken more and more into smaller and smaller pieces. Then only it's gonna be ready for the next process. Okay. When you talk about fabrication processes, you cannot run away from talking about hazardous chemicals. In a wafer fab, we have all the hazardous chemicals, we have all the hazardous gases, we have toxic gases, we have explosive, we have, you can see this, you can see the sign down there: explosive, flammable, toxic, peroxide, what else? Infectious substance, radioactive, corrosive, whatever you like. So if you talk about explosion of a wafer fab, for example, if you have a major explosion of a wafer fab, for example, if you talk about Siltiana and Kulim, then the implication is that Kulim will be out of the map. So that's the scale we're talking about. If you have a major explosion from a wafer fab, because you have everything there, right? So we have hydrogen, trichlorosilane, which are combustible. We have hydrochloric acid, super corrosive. We have tetrachlorosilane, highly toxic, environmental hazard as well. We have HF. You have dealt with quite a number of gases and chemicals, right? When you did your FYP. Siapa pernah deal dengan hazardous chemicals last time when you did your FYP? Were you aware that the chemicals or gases that you handled last time were hazardous? Ada deal dengan apa-apa yang hazardous? Syazwani ada deal dengan apa-apa yang hazardous during your FYP last time? Yeah, HCl, yes. So corrosive, you dealt with corrosive chemical. Lagi? Ada lagi? Siapa yang deal with some other stuff? HF, peroxide, what else? Sulfuric acid, hydrochloric, ada lagi? Yang lain semua tak ada deal dengan apa-apa ke? Anybody dealt with gas, hydrogen, nitrogen? Is nitrogen dangerous or not? Nitrogen bahaya ke tak? Nitrogen bahaya ke tak? Anis, Nor Anis, tak bahaya. Farah Azwani, bahaya kot. Okay, Fazira, tak bahaya. Okay, tak bahaya kan? Nitrogen kenapa dia tak bahaya? They inert, right? Is it? Right? It's inert. Tapi what happens if you stay in a lab, in a space, katalah you tengah buat eksperimen, you tengah buat FYP, and then dalam tu ada nitrogen, dalam ada nitrogen tank, you are in a closed space, kemudian nitrogen leak daripada tank tu, what happen? Is it dangerous? Nitrogen is inert, right? But then at this point, is it dangerous? You tengah buat eksperimen seorang-seorang dalam closed space, and the nitrogen tank leak. then you are all alone. Is it dangerous? Perhaps. What could happen? Fazira, what could happen? Kalau jadi macam tu, what could happen? That we know that nitrogen is inert. What could it do to us? Kita go big sikit nak just to put things into perspective about hazards. Apakah cannot breathe in oxygen, rest. Yes. Sesak nafas. Yes. It's called asphyxiation, right? Asphyxiation. Dekat tempat saya buat PhD dulu, UNSW, ada satu weekend ni, seorang staff, I'm not sure staff or student, dia kerja weekend. There's no friend or nobody, no other guys in the lab. So dia tengah kerja dalam lab, and then he was not aware. He or she, I couldn't remember. He was not aware that the oxygen depletion sensor was not working. So oxygen depletion sensor ni apa dia punya role? Dia nak monitor bila oxygen falls below certain level. Maksudnya, kalau kan you don't have oxygen to breathe, right? Kalau oxygen falls under certain level, tapi sensor tu was not working. So too bad, the sensor was not working, and then apa jadi? Apa jadi was he was so unfortunate because at that point of time ada nitrogen leakage in the room from the tank. So weekend, tak ada orang lain, dia seorang aja, right? And there's no sensor because the sensor was not working. So what does it mean? The sensor was not working, so that means no alarm. No alarm means he or she did not know that the oxygen is slowly depleted. So apa jadi? The room was filled with nitrogen, and then Monday morning, people came in, and then he's dead already. So dia dah mati on the floor, right? Asphyxiation. So walaupun you say nitrogen is not dangerous, yes, in fact it's not. It's inert in nature, maksudnya dia tak ada reaction. Tapi kalau kita berada dalam keadaan tu, then we will suffer from asphyxiation, then tak boleh nafas, then you could die. Right then and there, right? So yeah, so hazardous chemicals or gases are very, very dangerous. Dekat Siltera Infineon, there were a couple of times ada minor flames or something due to silane leakage. Silane is SiH4. Silane ni bahaya, senang terbakar. Oh, hold on. SiH4. Silane ni kita guna untuk apa? Kita guna untuk silicon deposition. Silicon thin film deposition. When you learn about CVD process later on, we're going to deal with silane in order to get the silicon from there and then to do the deposition as a thin layer. For example, amorphous silicon is usually originated from silane. So just one case to share with you. NUS punya solar lab, you can check this on Google later on. You can check SERIS, SERIS, Solar Energy Research Institute of Singapore, located in NUS, pernah terbakar the whole building due to silane leakage. That was in, I think, 2012 or 2013. So the building and in fact the research have to be shut down for 4 to 5 years. Sebab the whole building is gone, so equipments are gone, and then they have to repair and then prepare a new area, new equipment, blah blah blah, salvage whatever that's possible or buy new ones and restart the lab, and yeah, so it takes years. So waktu tu memang ramailah student-student yang tengah belajar were badly affected, right? So due to silane leakage. Silane leakage pun pernah terjadi dekat Siltera Infineon a couple of years ago. So but then there's no major injuries, just a small issue lah, small burn. Right. So my point is this. So when you talk about wafer fab, when you talk about either you're talking about front end or back end, so we are dealing with hazardous chemicals, hazardous gases. So kalau you pergi ke wafer fab, then you'll find, yeah, the most dangerous stuff on earth are there. to do the operation, right? To enable your deposition, to enable your lithography, your etching. In fact, photolithography, if you talk about the photoresist spinning itself, the photoresist itself is already dangerous. Walaupun di polymer, there are many more things inside there. So, but not to scare you off, chemicals and gases yang ada dalam fab ni, they are usually well contained. Well contained, that means they have double containment. They have all the safety features required for them to operate, right? Maksudnya tak boleh simply on. Even then, even with all the safety precautions and all the strategies, um, we still have incidents, right? We still have incidents, so we cannot avoid completely, but we can minimize with all the engineering skills or strategies we can do to contain the problem. But the if you talk about the processes cannot work without these hazardous chemicals and gases, unfortunately, right? Okay, so those are the things for today. Yep, lebih awal sikit sebab hari ni material tak banyak sangat. So tomorrow we're going to look into the conversion of polysilicon to monosilicon. Polycrystalline silicon from the rod, from the chunks, into monocrystalline silicon as a wafer, right? Okay, so any questions for today? Ada soalan? Can you guys follow so far? Tak ada soalan. So far you can follow, right? So far so good. All right. I've uploaded a few videos as well on the fabrication general, and then on FinFET technology as well just now from Intel on eLearn, and then you can watch from there. So it's very useful for you to understand the general overview of a wafer fab. Okay, with some hint of the technology that's gonna be fabricated for the recent applications. Okay, good. So far, so good. Then that's it for today. Tak ada soalan. And I'll see you tomorrow, inshallah. Bye-bye. Take care. Assalamualaikum.